Hi, this is Cheng Yi, and I did this local hill climbing algorithm with convolution kernels. For CDP versus time performance, the ideal case is that the curve starts with a fairly fast pace and slows down a little bit during the search, and finally saturates. In this case, heatmap 2 is better than heatmap 1, maybe because my algorithm suits heatmap 2 better, and it may also because that heatmap 2 has more of those higher value nodes, so it can maintain the fast pace a little bit longer. And this is the efficiency LV table. I think it is easier for heatmap 1 to gain access to those blue areas, those positive possibility nodes, but it is harder for it to maintain the highest possible areas. So it ends with lower values, but it starts with bigger ones. So and 900 is actually worse than 600 in my case. It is not good, but the algorithm can manage to maintain this value later on. And to think about the algorithm is an AI search algorithm, and the problem is an AI search problem. And the algorithm has the same idea as described in the paper, but I took a different approach when it comes to convolution kernels. It's slightly different, but the end result looks good. And there are some elements like those black barriers preventing our agent from going to certain areas, and it may result in graph 2, and this is actually pretty bad. That's why we need LHC convolution kernels to design the next step based on neighbors and neighbors of neighbors. So not just on the value of the certain nodes. So there may be some improvements, such as we can take direction into consideration. We maintain the direction of the last node. It may eliminate some of the unnecessary turns. And also, if we want to do a diagonal and 8-direction search, we need to consider those diagonal distances. It's actually longer than a normal 4-direction distance, so it may result in it may change our LV efficiency LV. So if we take distance and direction into consideration, and based on our LHC algorithm, we may build a model and have a more robust algorithm.